All right, so today we're going to talk about photovoltaic. We're going to talk about PV. So the first thing we should probably start with is what is photovoltaic? And so if we break that word in half, the photo and the voltaic part of that. Photo is the sun, and voltaic is electricity. So we're making electricity from the sun, is essentially where that comes from. And so this is a photovoltaic cell, or two of them actually. And we were just talking, this probably produces about 6 to 8 watts, roughly I would guess. This is a 2014, 2015 model, Solar World. This is a probably a 2010 model, I would imagine. So they have similar characteristics. Both of these cells, or all three of these cells, run at half a volt. This one is going to produce a little bit less amperage than this one because this one has more surface area. So the more surface area, the more amperage we're going to get, but they have an equal amount of potential. So the open circuit voltage is about 0.6 volts for both, and the closed circuit voltage is about, or the continuous voltage is going to be about 0.5. We're going to talk about the nitty gritty of the electricity, sorry guys, in just a minute so that we can figure it out. But I just kind of wanted to, while we're showing the video and I'm talking about the chemistry, I'm going to pass these around so that you have something that you can touch and feel and all that kind of good stuff. So I have about 200 to 400 of these cells that we can do lots of projects with, and we can get more if we want to. So I would really love to do something. So one of my dreams that I want to do, along with building that little solar advertisement that I was telling you guys about, chop into little pieces, is we could build solar concentrators for these, and we could figure out various different solar concentrators and try to break them, heat them up, and extract as much power we can out of them, and find out when is the point where they stop working, right? You know, how much heat can you pump into this thing before it just doesn't do it anymore? And then we can find out what is the optimal solar concentrator, and then we can try to figure out ways to cool them. So one of the ways we were kicking around the idea is the small one especially, but the big one, we could manufacture something, but the small one is roughly the size of an old Pentium 4 processor. And so what we could do is actually take the heat sink off of the back of a Pentium 4 processor and stick that on the back of that thing and heat up the front, and then we have this big active cooling fan on the back to keep the heat down. Because we can concentrate these PV panels and get more energy out as long as we keep the heat. If we don't get the heat, it degrades them a lot faster, and the life of them goes down really quickly. So other universities and scientific folk and tinkers have done this, and they use the concentrators, and they've been able to successfully do 10x, so they can get 10 times the amount of power out of those. So that would be an 80-watt cell with a small concentrator. Usually it's parabolic or trough. And some of them have got it up to 100x, but it just doesn't last very long. It lasts a few minutes, and then it doesn't work anymore. So I wanted to show you the chemistry of why that happens, because we're essentially building circuit boards that run on light, right? They use a very similar idea, very similar technology. So before we know how those suckers work, we need to talk about these suckers. So, Gary, I got your email, by the way.
Oh, yeah?
Yeah, I did. So I was kind of crunching some numbers, and so I'll go through the data with you too, because it's kind of
I
interesting.
found another one to send it to.
Yeah.
Basically on the same thing.
Yeah. So
Updated.
what I saw when I looked up at the USGS, they said 7.4 billion barrels is what they have there, and we're using 19.4 million barrels a day. So that comes out to be roughly about a year worth of usage.
Yeah.
So.
Well, they said 2,000 years or something.
Yeah. Now he did mention this like 2 trillion number, but I couldn't find any evidence for the 2 trillion. But I was just kind of, I wanted to, try to crunch some real numbers. So for the periodic table, first off, how many of you guys have seen this? Yeah, everybody. Okay, cool. That's a good start. So we have some basic qualities that happen with the periodic table. So we'll talk about some of this stuff here. So we have these numbers that are up here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 to 18, yada, yada, yada. What do those numbers mean?
Number of electrons.
Say it again.
Number of electrons.
The number of electrons and,
Uh,
but actually it's more specific to a different type. The outer shell, the valence shell is getting closer, okay? So let's talk about the inside of an atom. What's inside of an atom? Protons and neutrons. So the number designated is the number of protons, and then the neutrons are usually equal to the number of protons that you have. So in this case, we have manganese, and it or magnesium rather, and it has 12 protons and 12 neutrons. And to be able to make that stable, it also has 12 electrons. So the reason why I clarify that is because the protons is what designates the molecule, because we can have isotopes that have different number of neutrons, and we can have different charges that have different levels of ionization or whatever for the molecule. So if we had, let's pick on magnesium here. So if we had 13 electrons, would this be a positive or a negative molecule? It would be a negative, right? Because it has one more than the number of protons. And if it had 11 protons, or if it had 11 protons, it wouldn't be that anymore. If it was 11 electrons, would it be positive or negative?
Positive, you have more protons, right?
It'd be positive. Okay, so if something is positive, is a proton or an electron going to be attracted to it? An electron is going to be attracted to it, and the reverse of the other, right? So we can manipulate that identity that it's going to have, because electrons are free-flowing around the atom of the molecule, and it's going to want to exchange those electrons with each other to either share bonds in the place of covalent bonds. It's going to want to align itself into ionic bonds in the case of crystals and that kind of stuff, or it's going to rip electrons away in some cases, or give electrons, or share electrons. So what's weird about chemistry is we have all of these ingredients that we can use to make the cake, literally, but it's the electrons that are actually doing all of the handshaking and all of the stuff to be able to make it happen. So we worry a lot about, especially when we're talking about trying to produce electricity, how can we manipulate the electrons to be able to do what we want? And so to figure that part out, we know that we need to create some kind of, just like heat, if you have hot and cold, well, you can get a lot done with hot and cold to create motion, because hot will want to go to cold. So we can kind of do the same thing with the electrons. If we have a disproportionate amount, they're going to want to equalize with each other. And so we can manipulate that and put some kind of wire in between those so that it has to go through this long mousetrap to get to the other side. And so we're going to talk about how do we do that. So we have the numbers underneath, the letters that indicate the name of the element. So we got hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. How do we know what this number is? What does that specify? It's the weight, right? Or the mass of the object in grams. So this is in how many grams per mole is in an object. And so in this class, it doesn't really matter about the moles, I'll be honest. Later on, we'll talk about what the moles are. But in general, it's a really big something. Really, really big. So it's the amount of molecules in that really big something, and how much does that thing weigh, right? So in this case, hydrogen weighs 1 gram. This weighs 6.9 grams per mole, 22.9 grams per mole. And we can use that by measuring something on a balance and we can say, okay, this thing weighs 200 grams, and I know it's KOH. So I can then take K, 39.1, plus O, which is 16, plus H, which is 1, add those together, divide by the 200, and I know how many moles of the substances in that solution. And then I can know how to create a ratio. So if I know that, let's say I'm building a formula and I know I need 2 parts of this and 1 part of that, just like when you're cooking, I need 2 cups of sugar for 1 cup of milk. You need to know how much milk you have and how much you need to use so that you can make the ratios right. So this is our chart that we use to be able to make sure we know how to create the ratios. So on this side of the chart, we have the alkali metals, and these are the sexy ones that everybody is excited about because they explode in water. So these are the fun ones. So they have violent reactions in a scale of 10 as we go down the rows. So hydrogen actually doesn't react because it's just a gas, but these are all metals. And so from lithium to this gets a power of 10 more, power 10 more, power 10 in reactivity to water and other things, but mostly, a lot of times we use water, cesium and then francium. And so all of these things are stored in mineral oil or in a vacuum or something else that doesn't have moisture in it. So the reason why they get excited with water is because water is hydrogen, 2 parts hydrogen and 1 part oxygen, H2O. And when you have hydrogen, oxygen, and they're just naturally gases, and you light a flame next to them, they're the perfect combustible mixture that they want to come together to form water, and so they'll catch on fire and they'll cause a little pop, they'll explode, and energy will be released, that heat will fuse them together, and or not fuse them, that's not the right word because it's not fusion, but the electrons will change and they'll share and create water. So when we put this in here, what happens is they are very reactive, and they have a very reactive bond on them, so they pull those molecules to the side, and then when the water comes near it, it stretches them out, and then the heat that is released between those 2 molecules trying to rip it apart ends up catching it on fire, catches it on fire, electrons are moving, and then it causes a little explosion to a big explosion. So on this side of the chart, as we go further down the chart, we have more reactivity to objects. And on this side of the chart, we have less. So fluorine being the most reactive to being the less reactive as we work our way down the chart. Now you notice I didn't go all the way to the end. So why didn't I go all the way to the end? These are noble gases. And so what's important about the noble gases? They're stable, 100% stable. They don't want to talk to nobody, right? So we have helium, we have neon, argon, krypton, xenon, yada yada, and we go down the chart, and they have 8 electrons in their valence shell. And what's special about that is all of these molecules want to be at 8. So these are the ones who are Zen. They've reached their pinnacle and they're not interested in doing anything else. They're the lazy ones that just want to hang out. That's kind of anti-Zen, I guess. And then these guys over here, they are willing to give their electrons so that they can share. They are so depleted in their worth, I guess, that they want to share whatever they have so that they can become more like these 8 guys over here. So they have a tendency to want to share with these 7 guys that are so close to being Zen that they're so anxious that they'll react with everybody to be able to take as much as they can as quickly as they can, and are generally more reactive at doing that than those guys. And then, so these guys are able to give or share 1 electron. These guys are willing to accept 1 electron or share 1 of electron spaces in their home to be able to become 8, and everybody is stable and happy. So we have these rows are kind of like a spontaneous reaction stability feature. And we'll notice that as we go across, we have something like sodium chloride. So that is a 1, and this is a 7. 1 plus 7 is 8. And we have a stable molecule called sodium chloride. What is that molecule? Salt, right? So that's a really stable molecule. It doesn't hurt us. I mean, in the short term, you know, we eat enough pretzels and it's going to end up killing us, or probably chips for me. I love chips. And so over time it'll kill us, but in the short term we're doing just fine. Well, so the same thing can happen. So we have lithium, lithium bromide that can be produced. You can produce a potassium fluorine or potassium chlorine molecule, and those are stable, but they may not be healthy for you. So I'm not saying you should go out and mix these chemicals together and go eat them. But you can, generally speaking, share those two molecules, and they'll create a covalent bond and be able to share each other, or an ionic bond. And so that happens all through the table. On this side, we have they have one electron that they can share. These guys have 2 electrons that they can share. We're going to skip the middle because this is a different table. We'll come back to it in a sec. But then these guys have 3 electrons that they can share. These guys have 4, so they can either share or give. These guys can have a space to accept 3. These guys have a space to accept 2, and these guys have a space to accept 1. But the number of valence that they have is 7, 6, 5, 4, 3, 2, 1. So what do you think, by kind of looking at the chart, is something similar that you see? It's a little clouded because they're using IPAC instead of UPOC on this, but it's still there if you can see it. Okay, so the grouping. So we have this, and this is called Group A, and this stuff is Group B. So we essentially break those into 2 charts for this discussion, because these act differently than the rest of the chart does. But these guys have 1, these guys have 2, and if we skip over here, 3, 4, 5, 6, 7, 8. So that's the number of electrons that are in the valence shell of the molecule. And how that works is, so let's say that we have our our protons and neutrons inside of our atom here. Our first one, we have 2, and then we have 8 on the next one here. And then we have another one that comes out. Let's say it has 1, 2. We can tell a couple things about this. What do you think this molecule is? What's that?
It's one of the orange ones.
One of the orange ones. Okay. How did you know it's one of the orange ones?
The 2 outside, the 2 electrons on the outside.
Perfect. So you know, because this outer shell is called the valence electron shell. I'm doing it with orange again. You can't see this color. Okay. I will redo this on a different diagram. So you can see 2 here, and that correlates to this table. So now we add these up. So we say, okay, in the middle we have 2 for the inner. We have 8 on the outside, or the mid. Let's say we'll call that the mid ring. And then we have 2 on the end, right? So that on the valence shell. And so that gives us 12, right? So which one of these has 12? Magnesium. Okay, so magnesium has 12, so this gives us Mg. And we know that because it has the number of electrons there. If it was stable, now the tricky part is if this had 11, then we can't really tell by just counting the number unless we knew the number of protons that were in the middle, right? So then what base pair could work with magnesium to get it to 8? oxygen's a really good one. So we have this with this form all the time. We have magnesium oxide. And so on this side, we have 6 valence on this side, and it has 2 spots that's available. And those 2 spots fit perfectly in over there. So those 2 molecules come together, and they share those suckers, and now we have magnesium oxide. Now here's a question. Could it also be a magnesium sulfur bond or a magnesium selenium bond? It could, right? So if you were to do that, because it's at a different level than the other one, you would have to add energy into the system. So you'd have to supply energy to make those things and encourage the usage of that molecule.
When you say a different level?
On the row.
Oh, just.
On the row. So generally speaking, if you have something on this side, it will spontaneously react with something that is on a higher row, and then you need to add energy if it's on an equal row or lower. So it's a really, really rough way to calculate like spontaneity, but spontaneous reactions, but it's kind of a good like baseline thumb reaction. Another thing that may not matter here, but we're just going to talk about for a sec, is roughly whatever the number is, you can almost double it because you have protons and neutrons that roughly have most of the mass. And so you'll notice like we have 12, 24, 20, 40, 38, 87. You go over here and you have 13, 26. So they're in the ballpark of being almost double. So that's kind of helpful when you're working, when you're kind of like trying to reverse engineer a chemical. So what we're going to do here is we're going to add 2 more molecules onto this, or 2 more electrons onto this, and we're going to change this from manganese oxide to something else. So what is this molecule? And if you just want to tell me the letters, that's okay. Si. Okay. So Si is silicon. So silicon is a really good molecule for us. What do we use silicon for? Okay, but what are some things?
Lubrication.
Yeah, okay. Well, that's silicone, so that'll be the lubrication.
Dental work.
Yeah. How so?
Teeth guards, retainers, all.
Maybe. I don't know.
It depends on the processes they use, but I know some processes use silicons.
Okay. Have you guys heard of silicon wafers for like making processors and making transistors and all that kind of stuff? So we use in PV. If you look at these things, they're silicon wafers. That there's actually a coating on this too, which kind of like clouds the ability. But this is made of a silicon wafer, and we dope the silicon wafer with different chemicals to be able to produce some kind of electronegativity on top of it. And so if we use silicon, what's special about this as far as the group goes? It's in the middle. So it has 4 valence electrons, which means that it can either be a giver or it can be a taker. It's kind of right there in the middle. And so we have a really special name for this. They're called semiconductors. Because they only conduct half of the time. So we can manipulate semiconductors to be able to do our bidding. And so sometimes they're silicon-based, and sometimes they're germanium-based. As the bread in the situation. And most of these cells that we produce are boron and phosphorus cells. And so in this case, we put boron over here, and it has a 3 valence electrons. And on this side, this has 5 valence electrons. And so what does that do for us? If I have 3 here and I have 5 here, what's that? Yeah, so if we combine the 2, what does it make? It makes 8. And so because these guys want to share, they have to go between silicon to try to interact with each other to be able to make the cell work. And so we're manipulating it by building two electropolar materials so that when the light comes off, it's going to knock into some of those free electrons that are hanging out over there, and then it's going to, what's going to happen is it's going to jump valence is what's going to happen, and it's going to become freed for a second. Well, normally what would happen is it would want to become equalized again, and then it would go right back into the material. So what we do is we stick it on the silicon train and say, nope, we're going to take you for a ride. And then we grab that electron and it goes along through it hops on the silicon ride and it kind of is bumping all along. And then it goes through the wire, goes through our load, powers whatever we want, or charges the battery or does whatever. And then it returns. And then it comes to the acceptor, and it created a spot that was missing where it used to be, and then it fills that spot back up again. So we'll kind of see in more detail how that works. What's neat about this, though, is this is a complicated way to do it. If you guys wanted to build a solar cell at home, there's two ways you could do it really cheaply. One is if you have a piece of copper that's sitting at home, just a flat piece of copper sheet, you can take that and throw it on your burner at home, heat it up to 11. You guys saw Spinal Tap, you'll get that. And it will heat it up, and it's going to turn black on top of your copper plate. What you've created is a copper oxide and the copper metal that you used to have. And you've created a voltage potential between those, and that actually works as a solar cell too. So you can stick that in the sun, and it will produce milliwatts worth of power, but it will power something up for you. Another way that you can do it is if you have an old copier that's sitting around, really old copier, they have a piece of selenium that's in it, this guy right here. And selenium is able to absorb the sunlight and create electricity from it. So it creates an image. So if you had a piece of paper, how the old copiers work is you have a piece of paper, you put the light shines through it, the selenium grabs a shadow of whatever the image is, and anything that wasn't a shadow, it electrifies and creates grabs a bunch of electrons on top of the cell and kind of keeps it ionized. And then a piece of paper comes over with toner on it, and it transfers the image onto the piece of paper that is a positively charged paper. So you can also take that piece of selenium out, and it will work as a solar cell too. And then I guess a third way, just because I'm talking here, is you can also take titanium oxide and use titanium oxide as a photoconductor to be able to make electricity through that too. So we have naturally occurring things that happen that we can use. And again, so we have titanium oxide. So if you notice, it's still the same band that we're talking about. We have germanium, arsenic indium. So we have, and we have gallium. So this is a different type of cell that we can create. And so although these are the most popular type of cells, these are called monocrystalline cells. And so we have monocrystalline, we have polycrystalline, but they don't have to be crystalline. Like we also have thin film PV panels that work off of similar chemistry, but different materials. So then, I guess the beautiful thing about the industry that we're in is just because it's not made yet, doesn't mean that it can't be, that it's not the most efficient way of doing it. So there's a lot of really neat cells that are coming out based on the chemistry. Yeah.
Crazy idea. So titanium dioxide is amazing, right? It's really well used. You basically heat something with titanium dioxide with like magnesium and possibly get power out of it.
So it's not titanium dioxide, it's titanium oxide.
It is, okay.
So, but if you were able to take off the extra O, then you would have that potential difference, yeah. But yeah, so there are paintable solar cells. So there's these guys, they're not super efficient, but there's these guys that have solar in a can. And so they have it in an aerosol can, and you put the wires down on top of, they were doing it on a pizza box. You spray the solar material in a two-part process, and you let it dry between each one, and you put nail polish over the top of it, and now you have solar cells. That's like,
How efficient was it?
I think it's like 1% efficient. You know, but the efficiency is only matters because it shrinks the footprint. If you have lots of area, who cares about the efficiency, right? So.
If you painted your car, you could possibly rub it out all.
Right. Yeah. So if it was efficient enough, that's right. So the neat thing is there was another technology. Now I'm kind of just going off here, but there was another technology where 3D printing is becoming this really popular thing. And so they took and they said, hey, what if we could 3D print solar cells? And you can 3D print them. Now 3D printing usually is done in a like it has a Z axis on it so that it can raise it up. And they're like, solar cells are so thin that we don't even really need to do that. We'll just modify an inkjet printer. So they got an inkjet printer that has five cartridges in it, CMYK plus the extra black. And then they took those out, they cleansed them, they got new sponges for it, and they put their indium, gallium, arsenic, and germanium mixture in there. And then they just went through and they hacked a HP printer, changed the drivers for it, and they have really fine sputtering on it because our writing needs to be really, really good. And so they found that they actually needed more ink to go out than what was allowing it, so they had to modify the nozzle a little bit on the end by just, I think they said they hit it with a piece of sandpaper just to open it up a little bit. And then they just print one of the materials, then they wait a little bit of time, then they print another one, and they print another one. And so they printed out a sheet on butcher paper of printable solar panels that were like, I think they were 8 to 9% efficient, which is amazing. And so this I think she was 23 years old. She won a Nobel Prize for printable solar panels in 2011 or something. So there's such cool stuff because our technology we use for everyday stuff is pretty technological. Like everybody has a printer. How many of you guys have a printer that's sitting in the closet that you, or one that you threw away, took to the, everybody, right? Like if you have a $50 printer you've thrown away probably because you're like, oh, these inkjets, I bought the printer for $50 and this thing is $75 for the ink. What a hack, So when you're about ready to throw that out, look on the net and see if you can find some hackable software that you can turn into your own panel. So okay, so I'm going to kick up the video here. I'm going to play the silly one first, just so that we can have a little fun, and then we'll go into the other video in a second.
School, you're still at school. You can appreciate the sheer fun, mayhem that chemistry can be. There's so much to it. Bumps and burns, mixing chemicals. Fair enough. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. Anyway, next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkaline metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring
So I want you to notice each one of these increase in 10 times
Well, it might not look like
the reactivity.
But it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes! Oh, that is more like it. Only on breakdowns we get that kind of science. But I believe we can go one better. There is one more alkaline metal we can really use.
Yes, it's cesium, the emperor of alkali metals, particularly nasty to go off at any time.
That's it. Oh, yes. I like it already. Now, what's that going to do?
Is that your sweet? Yeah. Cool. No, I gotta go back and pay you guys. I just wanted to say hi. Oh, well, it's good seeing you. Good seeing you.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, frankium. But for some reason they wouldn't let us have any of that. So there you go. Today's lesson.
So there you go. So each one of those are increased in 10 times. So if you were able to get the francium at the end, or the francium, you would be able to see it explode 10 times that size. So that same gram of material that they're putting into the bathtub would explode the bathtub the size of this room, which is roughly the size of a paperclip.
That is a very explosive material.
Right? Isn't that interesting? So, what's that?
How rare are these metals?
Some of them are fairly rare, but these guys are a little bit more rare. But the lithium, sodium, potassium, rubidium, those are pretty common materials. So, you guys don't want to see any oil production probably right now.
No, we're still getting with the different wood.
Oh, you're probably over it now, right? We're talking about how do you make petroleum, so that's better. All right, so this next one is about how do these things work for real? So, and then we'll take a break. Or I guess I should ask, do you guys want to take a break now, or are you good?
I'm good.
Okay. Okay.
The hot surface of the sun radiates electromagnetic energy that spans the entire spectrum. The intensity of the light is greatest in the visible portion of the spectrum, and the warmth we feel on a sunny day is due to the absorption of infrared radiation. That warmth is energy. Conventional solar power uses that energy to heat water. The solar cells we will be discussing here convert that energy directly into electrical energy. It doesn't have to be a hot day. All we need is light. A clue to how they do this can be found by looking at the spectrum. A close look at the spectrum produced by the sun reveals thin darkened lines in the rainbow of the visible colors. These darkened lines are caused by atoms in the sun's and the Earth's atmosphere absorbing precise energies of light. These patterns of lines, like fingerprints, are called absorption spectra. The understanding of how atoms absorb and emit light reveals secrets of the electronic structure of the atom and is crucial for our discussion of the modern silicon solar cell. Niels Bohr proposed the first successful model of the hydrogen atom in 1913. It was a simple planetary model like the Earth orbiting around the Sun. A light negative electron in a circular orbit around a heavy, nearly stationary positive proton. Instead of a gravitational force, an attractive electric force holds the electron in its orbit. In order for the model to work, Bohr had to make a radical proposal. The electron can only occupy certain stable orbits with prescribed energies. The electron orbit closest to the proton has the lowest energy. Energy is needed to pull or lift the electron away from the proton, so orbits with larger radii have higher energies. If an electron is to jump from a lower orbit to a higher orbit, it will require an energy source. The energy source? Light. The electron can absorb a photon of light and use all of that photon's energy to jump from a lower energy orbit up to a higher energy orbit. Conversely, when the electron falls, it will emit all of its extra energy as a corresponding photon of light. It is simply conservation of energy. The energy of the photon is completely absorbed by the electron, allowing it to jump to the next energy level. Only particular photons can give their energy to the electron. That photon's energy must exactly match the energy required for the electron to jump. You may remember that there is an inverse relationship between energy and wavelength. So we say that the electron absorbs a particular wavelength or color of light in order to gain the energy required to jump energy levels. Let's look at an example. Say that the electron is in the second energy orbit. It can absorb the energy of a red photon and jump to the third energy orbit. When it falls back to the second level again, it must emit a red photon such that the total amount of energy remains the same. Similarly, an incoming blue photon will excite the electron into the fourth energy orbit. If the electron falls back, it will emit a blue photon, and so on. The result? The hydrogen atom can absorb photons of light with particular wavelengths or energy, and it can also emit photons of light with those same particular wavelengths. So for an excited hydrogen atom, we would expect to see particular wavelengths of light produced as the electron falls back and emits photons of light corresponding to those energies. This emission spectra of hydrogen is exactly what we see. Notice that only particular wavelengths of light are emitted, wavelengths that correspond to the required amount of energy to jump between levels. Furthermore, Bohr was able to calculate the exact wavelengths of the spectral lines of hydrogen in the visible region of the electromagnetic spectrum. What does this have to do with the sun? The dark lines we have seen in the sun's spectra are direct evidence that hydrogen atoms are absorbing energy from the sunlight. Why? Because they match, line for line, the emissions in the laboratory. These spectral lines become a valuable tool that we can use to learn about the electronic structure of the atom. However, while Bohr's model was extremely successful at predicting the wavelengths of light in the spectra of hydrogen, it failed to predict the light spectra in an atom with more than one electron. That success would have to wait for the birth of quantum mechanics. first papers that described quantum mechanics were published in 1926. They not only gave us a description of the atom when more than one electron is involved, they completely revolutionized physics and chemistry. The atoms of elements, other than hydrogen, contain 2 or more positive protons and an equal number of negative electrons. The number of protons identifies the element. You may recall that the positive protons are located at the compact center of the atom called the nucleus. Also in the nucleus are the electrically neutral particles called neutrons that will not enter into our discussion here. The electrons can be thought of as filling diffuse shells that surround the nucleus, similar to the orbits of the Bohr atom. The first shell can hold up to 2 electrons. The second and third shells can each hold up to 8, and so on. The modern photovoltaic cell consists primarily of silicon atoms. An atom of silicon has 14 protons. Of its 14 electrons, 2 fill the first shell, 8 fill the second shell, leaving 4 in the third shell. These 4 outer electrons are called valence electrons. They are important because they are involved in interactions with other atoms, as in the case of chemical bonds. But ordinary silicon will not help us capture and use the energy of the photons coming from the sun. We will need 2 other elements that are close in their electronic structure to silicon. The first is boron. An atom of boron has 5 protons and 5 electrons, 2 filling the first shell, leaving 3 valence electrons in the outer second shell, 1 less than silicon. The second is phosphorus. An atom of phosphorus has 15 protons and 15 electrons, with 5 of these valence electrons, 1 more than silicon. If we bring 2 atoms close together, the valence electrons from each atom will be attracted to the positive nucleus of the other atom. Pairs of valence electrons get shared between the atoms, 1 from each atom. This is the basic idea of a covalent molecular bond. Molecules are often represented with ball and stick models. The balls represent the atoms, and the sticks represent the bonds formed between their valence electrons. Molecular bonds not only hold atoms together to form molecules, but they are also responsible for holding atoms together in a covalent crystal. An example of a covalent crystal is a crystal of carbon. It has 4 valence electrons and crystallizes in a tetrahedral pattern, forming a beautiful gem, the diamond. Silicon, too, has 4 valence electrons. In a silicon crystal, each atom bonds with 4 neighboring atoms in a tetrahedral pattern. True, the silicon cell may not be a beautiful gem, but a crystal of silicon forms the jewel of modern electronics and our photovoltaic cell. For our discussion, we will simplify the representation of the silicon crystal. We represent the 3-dimensional crystal flattened to 2 dimensions. Each silicon atom, with its 4 valence electrons shown, is bonded to 4 other atoms. If we view our flat crystal along the edge, we see what appears to be a simple row of silicon atoms. Pairs of valence electrons form the covalent bonds between the atoms. Collectively, they form the valence band. Unoccupied atomic orbits with higher energy merge to form the conduction band. These 2 bands are separated in energy much like the regions between the allowed orbits in the Bohr model of the atom. This energy difference is called the band gap. And
Does this make sense what she's talking about, or is it getting a little fuzzy? It makes some sense? Okay. So I just wanted to clarify the conduction band they're talking about is if you were to continue to go out in shell level, this is where those valence electrons would jump up to get further away from that nucleus or the protons. Does that make some sense? So the further away from the nucleus it is, the more availability for it to become free-flowing it is.
refers to an energy interval where no electron is stable. Since the silicon atoms in the crystal are electrically neutral, we will indicate this neutrality by graying them out. Now, let's shine a light on our silicon crystal. If the incoming photon's energy is insufficient, the electron will stay in the valence band. However, if a photon of light has sufficient energy, a valence electron can absorb that photon, jumping up into the conduction band. It just so happens that such photons are abundant in sunlight. When sunlight strikes the silicon crystal, the photons are absorbed by the valence electrons, promoting them to the higher energy conduction band. Why do we want electrons in the conduction band? If electrons are in the conduction band, they are free to move and therefore can carry an electric current. Now, because the region the electron left behind was originally electrically neutral, the loss of the negative electron leaves this region positive. The positive region is called a hole. We will color it red for its net positive charge. Remember, electrons are colored blue here to designate their negative charge. Note that the crystal is still overall electrically neutral with the same number of positive charges and negative charges. However, electrons once promoted can spontaneously fall back into the hole in a process called recombination. If we are to use the energy of the electrons, now promoted into the conduction band, to power our electrical devices, we must first separate the electrons from the holes before they can recombine. We can accomplish this with an electric field. A simple example of this would be connecting a battery across the ends, say a positive terminal on the left and a negative terminal on the right. The positive terminal will attract the mobile conduction electrons so that they will move toward the positive side. At the same time, valence electrons move to fill the holes, leaving new holes behind. The result is that the holes migrate toward the negative terminal, and we have an electric current. But a crucial point for our solar cell is that we don't need a battery to create our electric field. A modern solar cell incorporates an intrinsic electric field that will separate our charges, giving us the current we need. So how do we create this electric field? A modern solar cell uses a p-n junction. Look again at our flattened, electrically neutral silicon crystal. We again show this neutrality by graying it out. Doping is a process where small numbers of impurity atoms replace some of the silicon atoms in the crystal. One can make N-type silicon by adding impurities, such as phosphorus with 5 valence electrons, one more than silicon. When in the crystal, 4 of its valence electrons form complete bonds with neighboring silicon atoms. This leaves 1 extra valence electron that will orbit the phosphorus in a Bohr-like orbit at very low temperatures, but will diffuse through the crystal at ordinary temperatures. A phosphorus atom is called an electron donor because it donates an extra electron to the silicon crystal. Because the phosphorus atom has one more proton than silicon, it has a net positive charge. We will color it red to denote this extra positive charge. One can make p-type silicon by adding impurities, such as boron, with only 3 valence electrons. It forms only 3 complete bonds with the neighboring silicon atoms, leaving one incomplete. This incomplete bond has the ability to capture an electron, usually a nearby electron from the valence band. This neighboring electron leaves behind a positive hole that can diffuse through the crystal at ordinary temperatures. With an extra electron near the boron, the region has a net negative charge. Because of this, the boron is called an electron acceptor. We will color the boron atom blue to denote its net negative charge. A p-type and an n-type silicon in contact with one another form what is called a p-n junction. Electrons from the n side diffuse across the p-n junction to the p side, and holes from the p side diffuse across the p-n junction to the n side. The electrons and holes can then recombine. The result is a net negative charge on the p side of the junction and a net positive charge on the n side, creating a strong electric field across the junction. Now, when we shine light at our p-n junction, an electron will be excited from the valence band into the conduction band, leaving behind a hole. This time, however, before the hole and electron can recombine to emit a photon, they are separated by the electric field created by the p-n junction. The negative electrons move to the positive region, and the positive holes migrate to the negative region. By separating the electrons from their holes, we have prevented their spontaneous recombination and loss of their excitation energy. Now we have all of the pieces required to construct our silicon solar cell. We start with a metallic layer, which serves as an electrical contact and as a substrate to support the rest of the cell. A thin wafer of boron-doped p-type silicon is laid down. Phosphorus is then diffused into the top surface, forming a p-n junction very near the top. With the p-n junction near the top, most of the sunlight will easily reach the junction. An anti-reflective coating is sprayed on the front surface to cut down on lost reflected light. Finally, front surface contacts are made to collect the electrons arriving from the junction. This grid is constructed with as few contacts as possible so that the p-n junction isn't shadowed too much. We can now power a light bulb or electric motor by completing the circuit. Our cell is complete. Photons of sunlight pass through the thin N layer. In the junction, their energy can be absorbed by electrons and excited into the conduction band, leaving behind positive holes. But before these can recombine, the electric field in the p-n junction separates them. The electrons move toward the front surface, and the holes move toward the back. Then they travel through the load and around to the bottom of the solar cell. The number of electrons that leave through the front contact is equal to the number of electrons that return to the back contact where they recombine with the holes. As more photons of sunlight are absorbed, electrons are excited into the conduction band and the process is repeated. No electrons are used up in the process. Photons give up their energy to create electron-hole pairs. The electrons give up their energy in the form of electrical power and return to the back contact of the cell where they finally recombine with the positive holes. It is simply conservation of energy, and the silicon solar cell should work, in principle, indefinitely. With no mechanical parts to break down, solar cells have operated in practice for 25 years or more.
Cool, guys. Tower, can you kick the lights back on there? So does that make some sense? Does that kind of help to add a little clarity to what's going on? I know it's dark room, heavy topic, lots of information. There's a chance of some dozing there, so I get it. Did you guys have any questions about? Yeah.
It makes sense how it works, but I don't understand how they make the boron doped silicon and the phosphorus doped silicon.
Oh, okay, so that's a little bit harder. So on a, actually, I might have another one for that. It's really quick on like how they do it, but I'll show it. So pretty much what they do is in a lab, they take the silicon crystal, and then on a nanoscale, they have to put the boron and replace it, and then they create a seed crystal. So then with that seed crystal, then they just throw it into a batch of silicon with the boron mixture, and then they heat it up into a big giant liquid, and then essentially they pull it out like a candle. And they pull out these huge reams of the boron doped crystal, and because the seed crystal helps to create the structure of the silicon, it aligns all the parts that they need to be able. So they start with one crystal that is designed a certain way, manufactured, and then it builds itself as it is being wound in a circle and then extruded out of this big machine. And then so they'll pull, in this case, they'll pull an ingot out that is this size minus, this was a circle at one point, and they chop these little ears off so that they could fit more cells in the grid. And so then they extrude this, and this thing could be, like 14 feet long, and then they go through and they cut it. I think I actually might have a video that shows that too. I didn't even think about that, but let's see here. Videos are always nice because if you can see the manufacturing of it, I don't know, at least for me, it makes a lot of sense. Let's see, I think it's this guy. Yeah, sorry. Is that good?
Raw silicon is melted at temperatures of over 1,400 degrees centigrade. A thin rod, known as the seed crystal, is then submerged into the liquid raw silicon and pulled back up very slowly. At this step in the process, the liquid silicon accumulates on the seed crystal and solidifies. Over 4 days, a silicon rod of up to 2.8 meters length takes shape. This basic round crystal, known as an ingot, is now cut into a rectangular shape. This is done for purely practical reasons. Later on, square-shaped solar cells can be installed much more effectively on the surface of a solar module. The ingots are cut into millimeter-thin slices using a very fine wire saw. The individual slices are called wafers and form the basis of each solar cell. Once the wafers have been cut, they are sent through a wash tub. This is because even the smallest piece of dust or dirt can compromise solar cell production. The wafer's surface is now very flat. Just like a mirror, many rays of light are reflected and can no longer be used to generate power. electrical conductivity. In a series of tests, the cell's conductivity is evaluated and sorted. Following the test phase, the solar cells are assembled. The cells are soldered together in such a way that the voltage accumulates. In a process referred to as lamination, the cells are assembled behind a pane of glass. As a result, they are protected from the elements for more than 25 years. One solar module contains 60 cells. When a number of modules are connected to one another, a solar power plant is created. And power is generated from the sun and the sand.
Is that pretty cool?
Yeah.
All right. Sorry, Tyler. You're gonna get your exercise, man. All right. So why don't we only got a few minutes, so why don't we just keep going here? I want to talk to you guys. We can go two different directions at this point. So we can talk about the types of solar cells that we have. So we can talk about monocrystalline and polycrystalline cells, and we have amorphous thin film. Those are kind of some of the big ones out there. We have one that has an acronym called SIGS, principal solar cells. And so I would send you guys next door so that you can do a little bit of research also, and we can come back and kind of talk about some of these cool ones that you found. And I'll give you the baseline ones. Or we can talk about the basic electricity side of how do we hook these cells up, which may actually be more practical, but I want to find out from you guys which direction do you want to go? Okay, you want to just see how you hook them up? Okay. You guys are like, I don't know, whatever you want to do, man. All right.
Make sure to do it in green.
I will do it in green. Oh, this thing's running away on me. All right. You see it? Okay. All right. So let's say that we need to talk about series and parallel cells is where this really boils down to. So we're going to take this all the way back to something that we already know, and then we'll relate it back to our solar cells. So you guys have used batteries before, right? You've probably used a battery in a flashlight before? Never. Okay, yeah, I know. This is pretty hard stuff. So there's two ways that we can hook these batteries up. So we can hook them up like this. Then we can hook them up like this. So we can hook these cells up in two different ways. We can hook them positive, negative, positive, negative, positive, negative to turn on a light bulb. And we can also hook them up positive, 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 negative, negative, negative to get those all hooked up. Okay, either way could work depending on the light bulb. But I'm going to throw something out here. Let's say that one of these batteries is at 1.5 volts and 1 amp, which is a standard alkaline battery-ish. And let's say that this light bulb can run at anywhere from 3.5 to 5 volts. And at let's say it uses 100 milliwatts or 100 milliamps. Which one of those systems do you think is going to turn the light bulb on? The bottom one? Okay, why so?
Because the top one's gonna be, the voltage is gonna be consistent because it's a series circuit,
Okay.
so it'd stay at 1.5 volts throughout the entire circuit. And the other one's gonna keep combining as it goes, so it's gonna be like 4.5 volts.
So your logic is right, but they're flipped. So I'm going to turn the projector off so you guys don't have to look through that. So in a series circuit, the voltage adds and the current is constant. And then in a parallel circuit, if this is voltage adds and current stays constant, what do you think the other one does? Okay, good. So the current adds and voltage is constant. So in these two circuits, this one is the series circuit, and this one is the parallel circuit. So what is this is the operating voltage of this, so we know that this is going to turn on, but how do we know that?
It's gonna be at 4.5 volts.
Okay, that's true, but how do you know that?
It says that the battery operates at 3.5 volts.
That's true. That's true. So, but you knew to do that because the series circuit adds voltage and keeps it stays constant, right? So this would be 1.5 volts times 3, because there's 3 of them that are positive, negative, positive, negative, positive, negative. That would give us 4.5 volts at. Okay. And then on this side, if we wanted to run this circuit, what's going on over here? 1.5 volts at 3 amps. Good. Okay. So I'm going to throw another thing out here. So we have this equation called watts equals volts times amps. Or EI. P equals E times I, if we want to do that also. But we're going to go into that in a second. So using this really basic one, volts times amps equals watts. How many watts does this equal if it's 4.5 volts times 1 amp? 4.5 watts. Okay. How many watts is this one? 4.5. All right. How do you know it's 4.5 watts? Because you multiply those two together. Okay, now I'm going to do something really, really complicated here. So let's take this right here. How many watts is this? 1.5, right? So another way to find out the total wattage, we could go 1.5 watts times 3 batteries. And that's going to equal 4.5 watts, right? So in either configuration, we can see that the wattage is always the same, but we can hook it up in different ways to be able to give us the outcome that we want. So what is the benefit of using this one to light this light bulb up? Yeah.
You don't need that much amperage to light that light.
Say it again.
Only need 1,000 milliamps to light that up. That series should last longer than parallel.
It's true, but why would we want to use this one instead of that one? You already said it, though.
Because you have a constant current.
Well, it has constant current, but it also is the operating voltage of the system. right? So the operating voltage of this light bulb is 3.5 to 5 volts. So we have to have it at 4.5 volts because it won't turn on. If I only had 2 batteries, that's not enough to turn it on. If I had 3 batteries, okay, now it can turn on. Now in this case, let's say that, will this turn on? It won't turn on, right? Because we're at 1.5 volts. We're way, way below what it needs to be at. So that is the golden rule when you're trying to work with, when you're trying to build a circuit. You need to build the voltage to operate the device. So that's one thing. And so the second thing is here, let's say that the operating voltage of this was 1 volt. Which system would I use then? That? The parallel one. Why?
It's going to turn on. It's going to use less voltage.
It will use less voltage and.
Toggle will have too much.
You got 1.5 volts, you only need 1.
That's right. And sometimes, if you give it too much voltage, you can actually blow it up. So in this case, let's imagine this is a 1.5 volt range. So if it was at 1.5 volts, it's probably actually going to be like 3 volts before it blows up. So this one would actually blow out our light bulb, and it would be too much power. So when we're talking about voltage, amperage, and wattage, one thing is they do different things. So I know we kind of talked about this the first day maybe, or the second day, I can't really remember. But voltage is going to be the force that pushes those electrons through the device. If your amperage is going to be the amount of electrons that are in there, and the wattage is the force that's pushing through times the amount of buckets of energy you have to give you a total amount of buckets. So if we were talking about this in water terms, your voltage is water pressure. Your amperage is the water that is in your pipe, in your hose. And then the wattage is your flow rate of that pipe. Does it make sense? Okay. Now it's not exactly flow rate because that would actually be your power, not your energy. Because when we say watts, that's an instantaneous. So really, in reality, it's the amount of pressure. If you were to take a snapshot inside the pipe, it's the amount of pressure times the square area of the amount of amperage or the amount of water that's in there. That would technically be what water is, but you can visualize the flow rate a little bit easier, I think. So I can at least. Okay, so I'm going to throw something out here. Can I erase this? Okay. So we're going to keep going with the idea of using light bulbs because we all know how to use light bulbs. Okay, so let's say that I have this system here, and I have 4.5 watts, and I have a bunch of little light bulbs here. Let's just use one light bulb for right now. And it's hooked to, let's do the back end of this series circuit here. Okay, so this is 4.5 volts at 1 amp. And I said that this is running at 4.5 volts because this is at 5 point, right? That makes sense. It's at 4.5 volts because that one is. And it's running at 100 milliamps. So a milli means what? 1,000th of the amp, right? So if we have 100 milliamps, what in amperage, what value is this? 0.1, perfect. So I'm just going to put 0.1 amps over here as a notation. How long will that light bulb run before those batteries are dead? So the voltage is pushing the amperage through this system, and how much energy is it using to be able to keep this light bulb going? 100 milliamps, right? So 1 hour goes by, 100 milliamps just passed. 2 hours went by, 200 milliamps, and it would run for 10 hours. How'd you get that number?
Just how many
There you go, yeah, so you said, okay, hey, I have 1,000 milliamps, because that's 1 amp, and I divided it by 100 milliamps per hour, and I got 10 hours. Would you agree with that? Okay, so I'm gonna do something super crazy here. Okay, now let's say that we're like, okay, we got 10, it runs for 10 hours and I'm good here. What if I put another light bulb in parallel with it? And it would have to be in parallel with it because, otherwise the series would do the same thing. We would have to have twice the voltage. We'd need to have, if it runs at 3.5, we'd need to have 7 volts to make that work. So we only have 4.5, so we'd have to stick these in parallel. That makes sense? So this would go over here. I'm gonna have another light bulb. Go like this, and then this would go over here like this, and that would go like that. Right? So these two batteries are in parallel with each other. So, or these two light bulbs. They both run at 100 milliamps. How long will this run?
5 hours.
5 hours. Man, you just did it like that. How'd you figure that out? You just divided by 2. Okay, so if you did 4 batteries, how long would it do? Or 4 lights? 2.5 hours. And if you did less than that, it'd be 1.25 hour, right? So we have this is good, right? We know how power is working. Okay, so now, like I said, if I put these two in series with each other, what would happen instead of parallel? It wouldn't run, right? Because now it's 4. We would need 3.5 volts plus 3.5 volts. That would be 7 volts. I only have 4.5 volts there, so I'd have to add more batteries to be able to make this thing run. Okay, so let's say that you're like, you know what? I really want to use these 3 batteries, but these light bulbs are just killing me. I'm using way too much power for them. So you say, you know what? I'm gonna replace these with LEDs. I'm really gonna be fancy here. So, and I stick in an LED here, and I stick the little resistor in there. Okay, and then let's say that this 4.5 volts runs that. We'd probably actually have to shrink this down to 2. So we'll put 2 LEDs in series with each other because we know we're good there. Okay, so we have 2 LEDs that are in our circuit, and they're both running at 4.5 volts. These LEDs use, let's say that they use 1 milliamp. They're 100 times more efficient than those other ones. 1 milliamp at 4.5 volts is what our system is running. This is 4.5 at 1 amp. How many hours does this thing run? How long?
1,000?
1,000, right? Yeah, so how'd you get that?
Because wouldn't the amperage,
But that would be just for one. It would be 500.
Oh yeah, 500. Yeah, you're right. Good call. Good catch. All right. So we took the 1,000 milliamps, which was our original 1 amp, and then we divided it by 2 times 1 milliamp, and we got 500. Per hour. 500 hours. Now, if they produce the same amount of light,
but
go ahead.
I thought that the current was constant if it's a series circuit.
It is. It is constant, but what's happened is we're using twice the amount.
Yeah.
So I said that they were, yeah. We're to make this 2.5 volts, 2.25 volts times 2. There we go. we shorthand when we were talking, so that's what actually happened. They were 2.25 volts times 2, because they're in series, would be 4.5 volts.
Okay.
They both run a milliamp, so they're running 2 times 1 milliamp to make 500 hours.
Okay.
Yeah. Good catch on both sides. Okay, so how does this room, oh, okay, I forgot something here. Now we're going back to this guy. Let's say that And instead, we trying to relate this back. If we have this at 3 amps, and let's just say for sake of argument that instead those light bulbs were able to be 4.5 volts, and these batteries ran at 4.5 volts instead of 1.5 volts. Okay, we're just completely screwing everything else up to keep it consistent. But let's say that this new value is 4.5 volts at 3 amps. These 3 batteries are in parallel, these are in series with each other. How long can this system run on those if they were equivalent? They'd run for 1,500 hours. 1,500 hours on LED in our imaginary system. So, one of the benefits to using series is that this will get you up to the voltage that you need. The parallel system provides the duration for which you want to run it.
As long as you have enough volts.
As long as you have enough volts. So once you hit the amount of voltage that you need, you use the parallel circuits to be able to increase the amount of capacity that you need to be able to run that. So how does that relate to if you're going to use solar and be off grid?
So once you reach the amount of, a larger amount of battery to store the size battery for voltage, the more you put parallel, the more power you're going to store, so the longer you're going to have power for.
That's right. So I'm going to use a really old school approach for showing how we would design an off-grid system that's like very, very rough for one thing. And it's also not really used anymore because this is a really expensive way to do it, but we're going to use it for illustration. So let's say that you guys know that those light bulbs and LEDs and your refrigerator, your TV, your microwave, all those things are called loads. Have you heard that term before?
Pull a certain amount of amperage off your system.
Yeah, that's right. So let's say that we have a usage load of let's just say 1 kilowatt hour, because we can simplify the numbers. That seems like not very much. Let's do 5 kilowatt hours in one day. So this is a really small house, right? 1/5 the size of a normal house. Could be a tiny house, could be an RV, could be, you know, just somebody who's really efficient. Maybe they have all LEDs and they don't use refrigeration, and you know, they have all kinds of good stuff going here. So I know what I want to power. For simplicity, these systems over here, these solar cells, they run on DC. Do you run anything in your house on DC? You don't, right? Everything is AC that you plug into the wall. Now you do have devices that actually are DC, but they use DC to AC rectifiers and converters and all that kind of stuff. So when you plug into the wall, it converts it from AC into DC, and then you run your electronics, usually down to 5 volts, 12 volts, 24 volts, or whatever the system is. But generally it's AC. So in a real system, you would use a AC. For our demonstration, we're going to use DC, because you can't actually use DC stuff. You have DC light bulbs, you have DC loads that you could use if you didn't want to use AC in the system. So we're going to talk about the simple one, and then we're going to talk about how we really do it. But this is illustration for basic electricity, so trying to full circle this. So let's say that this is actually using DC. A really common system that we use is 48 volt DC. Because the reason why when you're using off-grid systems we use 48 volts is because it's high enough to be able to shrink the wire size down, to be able to save on costs, and it also provides us with enough bang for the buck and all those kind of stuff. Yeah, I think that's fine. We can go there. So
when you say shrink the wire size, you mean from 12 volts or from 1?
yeah, so I'll show you the difference. If you So this is the power that we need to use, right? 5 kilowatt hours. So because watts equal volts times amps, well, watt hours also equal volt times amp hours that we have. And so if we have kilowatt hours, we have this amp hour requirement that we have. And so what we can actually do is we can take this and we can go 5,000 watts or watt hours and divide it into 48 volts, and we can get some value. What is, somebody have a calculator? You knew I was going to ask, huh? Thomas was already on it. It's like 104.2. Okay, now I'm going to do something else over here. So we go 500 watt hours and we divide that into 12 volts. What is that number? Okay. This is a lot of power just in general. And to specify here why this is wrong, we have 104 amp hours a day we're using. We're using 416 amp hours a day. So let's break this down a little bit further into what we would actually use over a whole day. We're going to oversimplify this a little bit. We're going to, I keep oversimplifying it. Now it's complicating it towards the end. So there are 4 suns a day. So as the sun goes through, our chart that you saw from Tuesday, well, there's 4 peak hours in that whole day. Sometimes we only have 0.2, then 0.3, 0.5, and if we added up all those blocks, it would add up to 4,000 kilowatt hours a day of sun that we would have. So in reality, this is going to be the solar system we would put on would not be a 5 kilowatt system. It would be 4 times smaller because we have 4 peak hours in our day here in Oregon. But for this simplification, it's fine. So we would use this amount of amp hours. The wire size of a wire that can fit 20 amps is a whole lot smaller than one that can fit 100 amps, right? And so as you can see here, as we increase the voltage, the amperage goes up or down depending on the voltage. So what we try to do in a house is we try to jack the voltage up as high as possible to keep it safe to be able to plug things in and out without actually having to turn off the switches like we should. But who does that? Who just unplugs stuff from the wall when it's running? Everybody, right? Have you been electrocuted when you've done that? No, right? So at 120 is that value that we can still provide a lot of power and still make it safe. But if that outlet was at 480, we could actually have wire sizes 4 times smaller and be able to save a lot more money. But if I was to pull that plug out at 480, you would have an arc that would go from your plug out to you, and you would be in the way and you would electrocute yourself. Or worst case scenario, it would actually explode and blow up your outlet and do an arc flash. So we don't do that. Well, the same thing happens here. So we try to jack it up to a safe voltage so that you can save money on your wires and not have to worry about it. So if you're using a 12-volt system, 12-volt systems are really, really small systems that use tiny wires because they want to keep you safe. That's what it boils down to. If you try to stick 5,000 watts into a 12-volt system, you'd have 416 amp hours that are available to do your action, which is great for some things, but that's some serious power you would have to deal with.
Is that why your vehicle runs on a 12-volt system?
No. So it runs on a 12-volt system because we have 12-volt batteries that run the car. So they don't want to add a lot of. If they went to 48 volts, you'd have half the wires. They could save half the price for everything, and you would have brighter headlights. You would have brighter stuff, but then they would have to spend money on rectifiers to be able to bring all the voltage down for your radio and for your cigarette lighter and all those other things that we don't want to do. So So in this example here, trying to figure out where we want to go. Do you mind, can I erase some of this? Do you guys care? Because I want to kind of normalize this a little bit, because it's way out of control. So let's say we do want to get to this 48 volts. We have 5 kilowatt hours a day. We know that there are 4 peak sun hours. So if we take 5,000 watt hours a day, and we divide it by 4 peak suns a day at 1,000 watts per meter squared per day, that's what that value of a peak sun hour is. We're essentially taking 5 and dividing it by 4,000. Does that make sense? What is that value? 1 point. A quarter? That's not right. 1 1/4. Or do.
It's 1 1/4.
Yeah, do 5,000 divided by 4,000.
It's 1 1/4.
1 1/4. Okay. Okay. I don't trust myself when I have this pen on the board. Like math just doesn't work up here, so I gotta make sure that everything is okay. So we're going to use a 1.5 kilowatt solar system to be able to power your house to have 100% usage during the day. Okay. So will this run your loads all through the day?
No.
It won't. Why? Not unless you store the power. So you're totally right. We have the availability to save all that energy. We have 1.5 kilowatts. We did all the math. It all should work. The problem we're not thinking about is this is only from 6 a.m. until around 5 p.m. Anything over 5 p.m., well, you better go to sleep because you're not going to use anything. So we need to build batteries to be able to build this system up. Okay, so we have this system coming in. This is how much energy is going into the system. We need to use this amount of energy for our batteries. How do we determine how many batteries we need?
At least get to 48 volts.
We need to get to 48 volts. So let's say that we found a super sweet battery. It has 6 volts and it provides 250 amp hours in that battery. That's a real thing. That's a T105 battery. If we have this for our battery, how do we get to 48 volts? We hook them in series, and how many would we do? We do 8, right? So we would go to find out the series side. Actually, I'm going to write here, so I'm going to draw here. So we're going to go series, and we're going to go 48 volts DC divided by 6 volts, and that's going to give us 8 batteries in series. At what amperage? 250. Okay, good. So then we have 6 volts, 250 amps. This is positive, that's negative, this is positive, that's negative. Like this. Boop. Boop. Okay. And then we have another one. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Got some terminals here.
You should teach your art class.
I know. It's pretty great, huh? And so this is negative, that's positive, so that one can go over here, makes this one positive, that one can go there. This one is negative, that's positive, so that can go there, that's negative, that's positive, so that can go there, that's negative. This is positive over here, negative, positive, negative, negative, positive. And now we have a positive over here and a negative over here that has a positive 48 volt DC. And we have the potential of a negative 48 volt DC, which, you know, if you're using your probes, you would see that. So, are we done? So how many watts are in in this battery? So we have 48 volts times how many amps?
250.
Times 250, and how many watts is that? 12,000? 12,000. Okay, maybe we are done then. How do we know we're done?
Because we need,
We only need 5,000.
You only need 5,000, right? So how many days can this run? 2.4 if you never have any sun ever again, right? So pretty much what you need to do is you need to withstand the 8 hours of no sun or 10 hours of no sun, whatever is the time when you get your first peak hour to be able to make that stuff work. So now we're done. We know everything's good.
But what if it keeps raining for 7 days like it's doing right now?
Well, yeah, so you're still good. So this is on average. So we get 6 during the summer and we get 2 during the winter.
Okay.
Yeah.
So
We're SOL for the next 3 days, because we're not gonna see a sunshine for 3 straight days.
Well, we're getting half of what the power is though.
Oh, so you're still drawing 5 a day.
Yeah. So we're still producing, we would be producing, what is that? 675 watts every day would be filling this battery back up. So this is a way that we can use our series and parallel math to be able to do something in solar. So are we done? We got 2 minutes. So I'm gonna just relate this real quickly back. These are half volt cells. So with the same idea, what would we do to be able to get these up to 48 volt panels? We'd put 96 of them in.
96 of them together.
That's right. So
How many
more.
are in each panel? 48 of them?
What's that?
How many are in each, like, large panel?
So that's where I'm getting at. So there's DC panels. So there's ones made for DC systems and there's ones made for AC systems. So the DC systems work off of 12 volts, 24 volts, 48 volts. So you would have panels that would have, for 12 volt systems, 24 cells in a system. For 24 volts, 48 volts in a system. For a 48 volt, you'd have 90, actually you would just hook up 2 24s together to be able to build that. But when you're doing a house, because you're working at 120 and you need that 300 volts that we were talking about earlier, you would have 36 or 72 of these in series in one panel to be able to get you 36 volts a panel. And then you would hook them in series, just like we did with the batteries, to be able to get them up to the desired voltage you need, not to run your loads, but to run your inverter in the house to convert it from DC to AC.
So 300 divided by 36, it's like the amount of panels you need.
Yep,
Just
in general, yeah. Does that make sense?
So if your house runs on DC, you don't need an inverter?
You know?
Oh, so that's what Europe has. It's so easy. Run on DC.
The only houses that run on
direct
DC.
current.
Well, they should be AC also.
I thought that.
A lot of them run off DC.
Yeah.
Really?
What do?
Oh, that's crazy. Houses in Europe run off.
I heard they run on 220.
Yeah, I think they run on
They're not-
220
They're not
versus.
DC, they're just a higher voltage. It's
A higher
different plug. They run
Yeah.
all their loads at what we run all our big stuff on. Like if you go to the cell phone,
Yeah.
you have to buy an adapter that has a built-in inverter.
A rectifier.
Rectifier.
Yeah.
Or you have to have a plug. A lot of old cell phones or older cell phones, a big brick,
Yeah.
will run 120, 240.
Uh-huh.
But you have to have the adapter because they use 2 huge plugs
Right.
into there. It's like when we went to Afghanistan too, if anybody who brought like TVs and stuff, because we're like the only country that does 110 and or that lower voltage.
Yeah.
We
Over
do
there.
a lot of things.
We had
Well-
to buy inverters for any of our American, inverters for any of our American stuff, bump down the voltage from 220.
Well, and the reason why is because you can save a lot of money on wiring too, you know, as you can, and 220 is still safe. We use 220.
For our washers and dryers, I use it for my air compressor and stuff.
Yeah, yeah. I use it for my car. Cool, guys. Well, thanks for taking the time with me. I hope this made some sense. We're gonna go over this a little bit more. We'll talk more about solar. If you guys are interested, I know some of you were eyeballing this tank up here. This tank, we're gonna talk about it in fuels, but this is a hydrogen tank that I use for my lawnmower. I know, I'm kind of weird running hydrogen through my lawnmower.
I'm gonna drive down the road one day, come run into it, and toys you over to your house.
I know, man. So this is it holds 100, it can withstand 100,000 PSI. You can blow this up with, there's drop test videos where they test this, where it gets blown up with dynamite. They shoot it with a 357. They freeze it to negative 20 degrees and try to blow it up with dynamite again. They drop it from 90 feet inside of a car to see what the impact force is. And in those cases, dynamite, 1/100,000th of an inch so it broke the resin in one of the strands of carbon fiber. And then in the drop test video, no damage except for a couple scuffs to the resin. In the case of the 357, 500,000th, so it went through a couple of the fibers, but it was still good. The only thing it didn't survive was the AR-15 armor-piercing round. And in that case, it vented out the hole, and then the pressure relief device kicked on and kept the tank in the same place so that it wouldn't fly all over the room. So, really, really safe stuff. I use them in my tanks, or I use them in my cars when I do conversions. So. Have a good weekend, guys. We'll see you soon. Oh, you got more for me? All right.
That's the same one.